Optimization is finding an alternative with the most cost-effective or highest achievable benefit under the given constraints. George Dancing, who was a member of the Air Force team during the Second World War, formulated the general linear programming problem as a type of optimization. Then, he created the Simplex algorithm as a method to solve the linear programming problems. In 10 years after linear programming conception, it was used in many fields: transportation, telecommunications, warfare, and much more. A linear programming problem can be defined as a problem of maximization or minimization of a linear function with linear constraints. These constraints may be equalities or inequalities. Let's discuss an example. We aim in this example to find the variables x1 and x2 to maximize the sum x1 plus x2 subject to the shown constraints. Any linear programming problem consists of the three essential elements of any optimization problem. The first is the objective function, which is the function required to be maximized or minimized. The second is the decision variables. The third is constraints that may include non-negativity conditions. Such a two-variable problem can be solved using the graphical method, by graphing the constraints equation and determine the feasible region, which is the region bounded by the constraints. This region includes the optimum point. Not all linear programming problems can be solved using graphical method, because there may be more than 3 decision variables. So generally, we can solve using one of the two standard forms: the standard maximum problem or the standard minimum problem. Any general linear programming problem can be converted to one of these standard forms.
Simplex algorithm is one of the methods to solve a linear programming problem in the general form. Let's illustrate the steps to apply the algorithm. First step: convert all inequalities into equalities by adding the slack variables. Then the constraints function would be as shown. Second step: write the objective function in the following form. Third step: construct the tableau in the following steps. The first row will be the variables distributed as shown. Here will be the decision variables. Here will be the slack variables. And here will be the objective function. The coefficients of the constraints function will be distributed as shown. The coefficients of the objective function will be distributed as shown. Let's have an example to solve the tableau. For example, we aim to maximize the following objective function subject to the shown constraints. By applying the first and second steps, we will obtain the following equations. Then illustrate the tableau. Then apply the iterations as follows. Determine the most negative in the final row. Divide the b vector's elements over the column of the most negative and then determine the smallest value. Then determine the pivot. Now apply the following row operations: R2 minus R1, R3 plus 4R1. After the row operations, we will obtain the following tableau. We will notice that there are no negative numbers in the final row. If there was any negative numbers, we will repeat the previous iterations till we obtain the final tableau with no negative numbers in the last row. Then, here is the final tableau. The optimum solution here, which represents the maximum summation, is equal to 520. So we have discussed the linear programming definition, which has led us to the simplex method. Now we are going to focus on its applications. It has many applications in real life, such as economy, and one of them is the cutting stock problem. So what is cutting stock problem? The CSP is the problem of cutting standard-sized pieces of stock material, such as paper rolls, glass, or sheet metal into pieces of specified sizes while minimizing material wasted. Customers usually order a certain number of rolls less than the standard width, and the manufacturer cuts the rolls into the required widths by slitting along the length of the metal. So, in your factory, you must reduce the waste materials to avoid the losses. To elaborate, let's discuss an example on the cutting stock problem. Consider metal sheets manufacturer, where rolls are produced in standard width of 210 inch wide, and there are order for 120 rolls of 60 inch wide, 200 rolls of 75 inch wide, 190 rolls of 90 inch wide, and 190 rolls of 110 inch wide. The basic cutting pattern feasibility constraint in this problem is that the sum of the widths cut from each stock roll must not exceed the standard width of the produced stock roll. We shouldn't exceed the standard width while cutting these orders, so we only have 9 possible combinations to cut the order efficiently. The first combination is to have one sheet of 110 inch wide and one sheet of 90 inch wide, and scrap will be 10 inch. Remember that our aim is to find the minimum number of patterns required to meet the demand with minimum scrap. We will use Simplex method to convert these combinations to equations of the objective functions and constraints. We solve them using Simplex method to achieve the minimum amount of scrap. It's not easy to solve it manually as we have 9 variables, so we have used MATLAB, which led us to our final results as shown.